Yeah, good day all. Welcome to Data Analytics from Theory to Practice. Today we'll be talking about penalized regression worked examples and looking at should you want to use pen and paper to solve some problems relating to penalized regression. Here present you some procedure. Now looking at equation 1, this is an example of a null model where we have the mean, then we have the error term. And we have so as I have equation 1, and the case of the error term is the error terms are independent, standard normal means 0, variance of 1, random variables. So we obtain the least square maximum likelihood estimator, and what we do is by minimizing the least square criterion, and the least square criterion is expressed in equation 2. Now looking at equation 1, this can be expressed as this to minimize the likelihood. So we have equation 2. Now, what we do next is to obtain the first derivative of equation 2 with respect to mu, which is equal to what we have here. Then we obtain which can be expressed after taking some like terms in equation 3. So by the time we solve, we yield the equation above, equation 3, and can be better expressed in equation 3. So, and the idea of doing this is talking about the bias variance trade-off. The bias variance trade-off is when we inject bias into a model, it reduces the variance, right? So it reduces the variance, and that's what the penalty does. By reducing the variance, by reducing the variance, and increase bias increases. So we have what we have in equation 3. Now, talking about biasness, an estimator is said to be unbiased when the estimator is equal to the mu, that is the mean. And we're looking at what we have in equation 3. We find the expectation of that, which is 1 over n summation expectation of y high. So we have 1 over n when we have y high, when we sum it, the expectation up to n, we are going to obtain n mu. So now we have our mu. So which means is unbiased. That is when the penalty has not been introduced, is unbiased. Now look at the variance of the estimator. Also, we can see that our variance after being worked, we obtain 1 n over n squared, which is 1 over n. Now we now consider this is a, at this point, variance of 1 over n is we square what we have. 1 over n we squared, it comes to the back. Then the summation y high, variance of that is actually n. So, and that's where we have 1 over n. Now I want to add penalty to it. Penalty to what we have in equation 2 here. Now we call this one least square. This one is the ridge approach, and they will now obtain equation 4, which is the one in red is the penalty term. So we do the same. We find the derivative respect to mu and set to 0. So we obtain it. We take the like terms. Then we now have our mu regression, as in ridge actually, is now equal to summation y high, where I goes from 1 to n, all over n plus lambda. So we can do this mathematically and see what we are going to obtain. Which means that the expectation of mu2, which is actually the mu r, is equal to what? N all over n plus lambda. So multiplied by our mu, that's what we have. We can see that the ridge regression estimator is biased because the left hand side is not equal to mu, which is supposed to be in the case of biased estimator or unbiased estimator. Now this one is actually biased. Now how do you want to quantify the biasness? We now have our bias is equal to Mu2 cap is equal to this. By the time we bring it in, we can see that supposedly, if it's unbiased, the expectation of mu cap 2 minus mu should give us to 0. But in this case, it's not equal to 0, and therefore we can see that what our bias gives us is minus lambda mu all over n plus lambda, and which is not 0, as I mentioned earlier. So now we can now see that the variance also, we can see that the variance, when we compute the variance, we can see that the variance is less compared to that of least square. That is why we have the variance here. This is the variance for the ridge regression. Now let's look at the variance for the least square. You can see that is 1 over n. And we can see that this is actually less than this mathematically. Therefore, since for lambda greater than 0, we get this, and which is less than that. So by so doing, we can see that introducing the penalty into our model reduces variance, but increases bias. And to make our model efficient, our estimate to be efficient estimator, we need less variance. A model that has a less variance is more efficient than a model that has higher variance, and that is why we talk about efficient estimator. An efficient estimator. So an estimator that has a less variance actually gives you a better. And now look at it, the sweet spot between bias and variance can be achieved by the choice of penalty parameter lambda. This is typically done with cross-validation aiming to minimize the test error. So with this, we have been equipped with how the what actually beyond the model. This gives us a practical explanation of how penalized regression works or model works. So if you have any question you can ask, go to the comment section and ask your questions. I'll be willing to answer you. I have some other examples or problems that can be solved, which we could do in the next session. So I want you to, don't forget to comment, as I said, ask a question, subscribe to this channel for more videos. Welcome to Datalytics. Thank you. I'll be looking forward to hearing from you.